we'll have another little 5-minute presentation from an engineer from Procter & Gamble, who is also, they're also recruiting. You think of Procter & Gamble as being mostly diapers and toothpaste, but they in fact do a lot of engineering, serious electrical engineering. So to get back to the topic here, anybody try building this small computer over the weekend? Time's wasting, folks. It's a 2-week lab. Anybody try it? Okay. I had a couple of questions on Friday which suggested I should go over this process a little bit more. And so there's at the center of this, well, there's some Verilog which defines the CPU, which you're going to, of course, feed into Quartus to compile. There is some source code in this as yet unnamed language. Does anybody come up with a clever name for a stack language? Stackable. Stacky? Stacked? I don't know. Think about it. You know, maybe we ought to have a contest. So source code feeds into a MATLAB program, which is the compiler. And this MATLAB program has exactly one parameter. You run it, and it opens a dialog box that asks for the name of a file. Okay. MATLAB compiler then output is a star.mif file, which you have to identify to Quartus by means of the synthesis directive that we talked about on Friday. And once you have identified the MIF file to Quartus once, then you can do this compile, generate MIF, modify in Quartus without going through the whole system generation, but rather bypassing the system generation and just updating the memory image file. So it's a fairly fast compile, run, test sequence. Are there any questions about this? It seemed like there's some obscurity on Friday. So I think by the Friday lab, you should have a CPU running with your own code on it. There are examples on the stack CPU page that include the basic compiler, of course. An example which implements in software implements a string print capability and implements a UART so that you can debug. So it'll print, if you hook up a serial cable to the FPGA and take it over to the PC, then you can use a terminal emulator on the PC, typically PuTTY. Familiar with PuTTY? PuTTY is a free terminal emulator, freeware terminal emulator. You can go from the serial output on the FPGA to the PC, and you can view the output of your computer in PuTTY. So it's useful for debugging. The string printing capabilities are not fantastic yet, maybe that'd make a good final project. How about somebody implement Ethernet for this processor? Anyways, I see a couple of people holding their head. I don't think it's that bad, but it'll probably be a little bit messy. But but the existing serial I/O prints integers, 18-bit integers. It accepts 18-bit integers from the keyboard in hexadecimal format, and it prints arbitrary strings. So with that, you can probably debug. It's not supposed to be a very high-level interface. It's supposed to be a debug interface. I also implemented another example which hooks the small processor to the VGA system so that you can do graphics. And so in principle, you could make a text interface so that you could debug with text on the screen, but I haven't done that yet. The most I've done is to do particle simulations, physics simulations. Doing physics simulations, doing a simulated diffusion system, you can animate about 1,800 particles at about 120 frames a second. So it's cranking right along. But get started on this. The only way to ask questions about any topic is to have worked with it. You need to work with it like now, so that by Friday you have something running. One last piece of the CPU I'd like to talk about is the multiplier, because I think you're going to have to modify that. And the reason you're going to have to modify that is that I wrote a multiplier which is a 10.8 multiplier, which means that it carries 7 bits of fraction and 10 bits of integer, actually 9 bits of integer, because you have a sign bit here. 2's complement 10.8. 10.8 format. This was good for graphics because I could map the integer part of this representation into pixels on the screen, and I could map this part of the integer, or the fractional part, into fractional pixels so that I could have a velocity of less than 1 pixel per frame. What you're going to find that you need for DSP is a different format, because 8 bits of fraction just won't quite work for the filters I'm going to ask you to build. You're probably going to need 14 or 16 bits of precision, and so you're going to have to modify the multiplier. The existing multiplier. Now, this doesn't mean you have to modify the CPU in any way. You do have to modify the multiply primitive, and you don't even have to modify the compiler, because the only thing that changes here is how you interpret internally, how your brain interprets the integers. So the multiply module has just 3 parameters, an A and a B input and an output. And because we're using an 18-bit system, you might guess that this would be an 18-bit output, and you'd be right. And again, the inputs are 18 bits. We also need a couple of internal states. By the way, this multiplier is combinatorial. There is no clock on it. We're going to need we need a wire signed 35 down to 0. We need a 36-bit product of two 18-bit numbers. So we need a wire which is going to be an internal signal that does not go to the outside. We're going to assign mult out equal A times B. Well, that's handy. The asterisk, the star operator in this version of Verilog in Quartus 2 will instantiate a hardware multiplier for you. Okay. Yes? Say again? Yeah. The output out is 18-bit. No, because the value returned has to be in the same format as the inputs. And so we have to do some bit manipulation here, right? So, as long as there are still manipulators, as long as there are still multipliers left on the chip to use, the asterisk will instantiate a hardware multiplier for you. It uses multipliers. Alex?
So is the format of the hardware that instantiates going to be 20 bits of integer and 16 bits of fraction? Just doubles.
It doesn't know anything about bits. So it's just going to do a integer multiply, and you have to force it into the right format by choosing the correct output bits. So the next step here is to say that if we have two 18-bit numbers that are in 10/8 format, then the output of this multiply is in 1620 format, and what we have to choose as the output are sum of the bits. In fact, we have to choose bit 8 through 15 as the fraction, and 16 through 24 as the integer part, and bit 35 as the sign. And so, yes, it can overflow. And you can't allow that to happen. So here we're going to assign the output value as the concatenation of mult out bit 35 concatenated with mult out bits 24 down to 8. So 24 minus 8 is 16 plus 1 is 17 plus the sign bit is 18 bits. So we multiply two 18-bit numbers, we get an 18-bit result, which we can store back into memory. Absolutely. Everything's a compromise. You're quite right. Accuracy is compromised. You're losing all of the low order digits. So accuracy is compromised. Overflow is compromised. You're losing all of the overflow digits. So for DSP, where accuracy very much matters, you want to save as many bits as you can. So going to 2.16 might make a lot of sense, where you keep much more of the fraction. But you're going to have to make that decision depending on how much accuracy you think you need. And you'll be able to tell, because if you don't keep enough bits, the filters won't work. Now, I wrote a MATLAB program that allows you to simulate the effect of finite filters. And you should do that pretty soon also, because you're going to have to make a design decision about the multiplier. You don't necessarily have to change the multiply instruction. We're going to talk about this pretty soon, maybe this lecture, maybe next lecture. But there are various ways of implementing digital filters, some of which don't require as much accuracy as others. The ones that don't require as much accuracy require more arithmetic. And so you'll have to write a longer code. It's up to you. Any questions about this? So, I'm only going to ask you to change one. Well, you're either going to have to change one instruction in the CPU, the multiply, or you're going to have to look at second order sections. You're going to have to look at factored transfer functions. But I think one way or the other you're going to have to, probably the easiest thing to do is to modify the multiply command. I toyed with the idea of having you write an interrupt service, interrupt hardware module, or adding instructions. But if you add an instruction, then you have to modify the compiler and the assembler. And I didn't think that I wanted to get into that. I doubt if you do either. Well, you can hack on the compiler all you want. Any questions? So maybe a good waypoint for Friday would be to have an operating CPU with a modified multiply routine and being verified with some arithmetic that you can print out on the terminal. Any questions? All right, so let's start talking about the audio codec now. So the CPU, the generic CPU that you're going to be using, has 4 input and 4 output channels, each 18 bits. And what I'm going to ask you to do is to loop the audio codec through the CPU. The audio codec produces 16 bits of 2's complement input. So you're going to have two channels, left and right, of 16-bit 2's complement. Each one of these is going to go into its own CPU because you're going to instantiate two of them. And then this is going to go back out to the left and right channel of the codec. And this is also 16-bit 2's comp. So we have to do a 16 to 18 conversion and 18-bit back to 16-bit conversion, but that's easy. What I want to do first, though, is to look at the hardware functions of the audio codec. Wow. We use old technology here. This particular technology, though, works much better when you have chalky hands than using a keyboard. So, wipe some of the dust off some of the lenses and focus that thing. Wow, what's that spot? That's a Coke can that was set on the projector. That's better. It's not perfect, but it's better. Can you see that? Is it too small? Darwin, you want to hit the front lights over there? This is how we magnify this old technology. That's what we call the zoom control. We can zoom it back one more, but that's probably as big as we can get on the screen. So, this is a chip. This is a piece of hardware on the DE2 board. All of these connections on the bottom go to the FPGA. All the ones on the top go to the FPGA. And the ones on the left and right go to physical connectors on the board that you plug stuff into. So line in, right line in and left line in is a standard 3.5 millimeter phone jack. Mic in is a separate 3.5 millimeter phone jack. Mic bias is an output on the same phone jack. This would be, and then right HP out and low and left HP out are the right and left channels with gain control that are brought out to another phone jack. Let me see, that would be usually the green one, right? Typically an output. And let's see, this is the pink one, I think, and this is the blue one, typically if it's a PC or a laptop. So you can connect stuff to it. What I'm going to ask you to do for this particular lab is to connect different stuff to this input, signal generator for testing, plus the output of some music source, PC, whatever, Pandora, your MP3 player. Oh, that's so 20th century. And then hook the output to the speaker so you can listen to it for testing. Or hook it back to the scope, of course. And the connections on the top, S clock and data in, are bidirectional ports. In this case, we're going to use the FPGA to determine the S clock, and then the FPGA and the control interface are going to have a dialogue over the two bidirectional data bus. 1 bit, it's a serial data bus, to set up this chip. So when you reset the board, when you turn on the power, there's going to be a dialogue between the FPGA and the Wolfson chip to determine left channel gain, right channel gain, left channel mute, right channel mute, a whole bunch of parameters, 10 or 20 parameters. This particular interface is called an I2C interface, or sometimes I2C. It is a standard industry interface for low-speed serial communication. And mercifully, Thoracic implemented an I2C communication module for you, so you don't have to implement that yourself. So at reset time, your hardware design will start up a state machine in a I2C controller that will configure this chip. Now you can redo that at any time if you want to make, say, a gain control on the left or right channel, but typically for these labs you do it once and then you don't mess with it anymore, except when the state machine, your state machine running on the FPGA, gets out of sync with the state machine running on the Wolfson chip, which happens moderately often. Then all of the high-speed data comes through these lines. ADC data comes from the analog to digital converter. So your line in, your mic in, all come through the ADC converters and end up at ADC data. So you can read those from the FPGA. There's an ADC left-right clock, which synchronizes the left and right channel with what's being read or written to the Wolfson chip. That, in this case, is going to be generated by the FPGA. There's a bit clock, which is much faster. I'll talk about in a minute. A bit clock that will synchronize the serial transfer of data. And then there's a DAC data, which is going to be generated by the FPGA and goes through the audio interface and out through the DAC to the output. So the flow of data will be our line in through the digital filters, down into the FPGA, back out of the FPGA through the digital filters through the DAC. All of these settings are controllable. Volume in, mic boost, mutes of various sorts at the output, analog bypass that allows you to just take the input and take it to the output without going through the digital filters, so that you can actually mix the raw input with the filtered output if for some reason you wanted to do that. It's a very flexible chip, and whenever you hear the word flexible, you can convert that one-to-one into complex. Any questions about this? Quite often, 5 times a day, quite often you will find when you're using this chip that the bit clock gets out of synchronization with the left-right clock. And so part of the data from the left channel will end up in the right channel, and part of the data from the right channel will end up in the left channel, which makes very ugly waveforms. And the only solution to that is to cycle the power. This kind of behavior encourages superstitious behavior in students. Superstitious behavior being you cycle the power no matter what, just in case. But that's probably only rational here. Darwin, yes.
So since we don't have ISRs, how are we going to do this?
Good question. How are you going to do the synchronization?
Sure, we need those IO points.
Yeah, so how are you going to do? So it's all right, so let's talk a little bit more about this DAC left-right clock. DA, want to hit the lights again, please? So the FPGA is going to generate a DAC left-right clock, which it turns out is high on left channel and low on right channel. And the bit clock, BCLK, is going to transition a bunch of times on the left and right, enough that you can put out 16 bits, most significant bit least significant bit. You can put out 16 bit times on each channel. And this, by the way, would and then the data actually comes out on DAC DAT. Would suggest that about every edge here, at approximately every edge, you're going to want to have your CPU polling for the edge of this waveform and load a new value into a hardware register, which then gets pipelined into the audio codec on the next cycle. So the way I'm seeing the synchronization is by looking at the rising and falling edge of DAC left-right clock. Whenever you poll on a CPU, you're assuming that you have enough cycles that you can poll quickly enough that you don't miss the event. So we have to ask, how much time do we have here? Well, this whole distance, this whole time at 48 kilohertz must be about 22 microseconds. And so you have to get a new edge on each of the two CPUs. You have to get a new edge each 22 microseconds. Remember, one CPU is going to be doing the left channel, another CPU is going to be doing the right channel. So each CPU has to notice an edge in about 22 microseconds. If you run the CPU at 50 megahertz or so, that means you have something like 1,000 cycles to calculate the filtered sample and to get back to the wait loop where you're going to be detecting the edge as fast as possible. That seems doable. 1,000 cycles is a lot of cycles. So I don't think there is a very strong synchronization problem here. I think you have plenty of time to do this calculation. Any questions? To find the code for the audio codec, you're going to want to go to example number 1 on the ECE 5760 page DE2 FPGA DSP HTML, and the capitalization obviously matters here. That's uppercase. This is uppercase, DE2. This page is directly linked off the 5760 page, and I'll normally just call it the DSP page. That's its title on 5760 pages, FPGA. The title on the link is FPGA DSP. This example includes several chunks of software. It includes the DAC, the ADC DAC interface. It includes the low-level I2C controller. It also includes the state machine generator that generates the sequence of commands and bits to program the control interface. And you'll need all of it, which is conveniently zipped together on in that example for your downloading pleasure. I don't think it's particularly necessary to go through the state machine that initializes all of the control interfaces. But if you look at the Wolfson documentation, you will find that each one of these controls, as documented on this sheet, has a register number next to it. That says register 0A, register 80, register 00. You can look up in the Wolfson documentation how to modify all of these parameters if you care to. The module audio ADC DAC, actually DAC ADC, I guess, is my hack of the thoracic hack. Yeah, I see some half smiles and some winces. What I did was to simplify away all the stuff that I didn't think was necessary from the thoracic version. The thoracic version allows you to take audio off of SD card, out of flash memory, or out of RAM. I modified it so that it has precisely one source, and that is the calculation going on in the FPGA. This simplified away a whole bunch of address generation junk I didn't want to deal with. So my version of this, which is what you're going to want to use, has an output OAUD underscore bit clock. This is an output from this device through the FPGA. No, I'm sorry. This is an output from the FPGA to the hardware audio codec, and then an output to the codec, which is the data line. An output to the audio codec, which is the left-right clock, and an input from the audio data, from the audio chip, which is the ADC data. There are 2 inputs and 2 outputs that your code is going to have to manipulate. Output AUD in left and output AUD in right. It's an output from the standpoint of the audio codec. It's an input to your code because it's the ADC data. There are two more outputs from your code called in AUD and in AUD external right, which are going to be the audio that you generate that gets sent to the DAC. So I don't foresee you having to mess with these I/O channels, but you're going to have to grab these 2. You're going to have to take these 2 channels, route 1 to each CPU, do your digital filter operation, and then output them back to these 2 channels. One thing you're going to need to pay attention to a lot in this lab, because there's going to be some fairly long paths from the audio codec through your CPU back to the audio codec, is you're going to have to pay attention to the timing analyzer. When you do the compile, you may have noticed that there's a compile status panel that appears in the Quartus 2 window. Have you looked at that? Tells you how many blocks have been used and how many multipliers have been used and all that kind of stuff. You looked at that? Okay. To the left of that panel is a menu. If you click on the timing menu item, it'll pop open a submenu, and if any of those submenu items are red, you're in trouble. That means you have a timing violation. That means you tried to get a signal through the chip in a negative time. It's not good. So, said differently, you need a negative delay someplace. So, if you start getting strange behavior of any sort, in fact, in general, whenever you compile something, you should look at the timing analysis and make sure that you haven't violated reality, haven't violated causality. That you don't have a design that cannot be fabricated because of timing errors. When that happens, you have to do something. You cannot ignore a timing violation. It'll compile successfully. It says there are no errors in the Verilog, but if you have a timing error, it may not work right. And so you have to look at the timing and you have to fix it. Now up in the Tools menu, there's a timing analysis advisor which suggests some of the things you can do to get rid of timing errors, and you should do those. Timing errors in this case will come out as distorted audio. You'll know it when you hear it.